Hi, everyone. Thank you again for joining us for Scaling Up Data Center Management with the NVMe-MI 2.0 specification. I'd like to take a moment here to introduce you to our speakers. Today we have Austin Bolen, who is co-chair of the NVMe-MI Workgroup with Dell, and Myron Loewen, an NVM Express board member for Solidigm. With that, I'll go ahead and pass it off to Austin to kick off the webinar.
All right. Thank you, Nolan. And good morning to everyone, or good afternoon or evening, depending on where you are. Just wanted to welcome everyone and thank everyone for joining the webinar. So I'll start out with a very brief overview of NVMe-MI, and then we'll jump into the changes we've made in the MI 2.0 spec from the prior revision, which was MI 1.2. And was released back around 3.5 years ago. And then I'll cover a bunch of interoperability enhancements that we made and cover the support we added for asynchronous events. And then I'm going to turn it over to Myron to talk about high availability and I3C basic. So this will be a very brief overview of NVMe-MI just to set the stage. If you'd like to get a more in-depth overview of the fundamentals of NVMe-MI, I added a link in the references section of this presentation to a prior webinar that covers all that. So what is NVMe-MI? The soundbite that sums it up is that it's a message-based programming interface for managing NVMe storage devices or NVMe enclosures. And by management, I mean operations such as inventorying, which includes the ability to discover components in a computer system and discover the type of each component along with their supported capabilities and features. Monitoring, which allows you to monitor things like drive health, temperature, endurance wear out, and so forth. Configuration, which allows changing configurable options or performing operations on a component. A couple of examples in NVMe would include creating namespaces or formatting a drive. And then we have firmware updates, which provide the ability to update NVMe drive firmware so that users can ensure they have the latest bug fixes, security patches, performance improvements, and so on. Now, the primary focus of NVMe-MI is on out-of-band management, where out-of-band in this context just means the management entity is running on a BMC completely independent of the host operating system that's running on the host CPUs. Out-of-band NVMe-MI utilizes an industry standard transport called MCTP that's defined by DMTF. And NVMe-MI also utilizes an industry standard vital product data format defined by the IPMI specifications. And the diagram on the right shows all the various out-of-band management traffic flows. So a BMC can manage an NVMe storage device out-of-band over a sideband bus, such as SM bus or I3C, using NVMe-MI over MCTP as shown by the light blue line on the far right of the diagram. Or over PCI VDM as shown by the brownish colored curved line there. A BMC can also read vital product data over I2C utilizing the data format and access method defined by the IPMI FRU spec as shown in the dark blue line on the right of the diagram. And finally, NVMe-MI also supports the ability to tunnel management commands in band from the host operating system running on the host CPUs, as shown by the gold line on the left of the diagram. Okay, so one thing we did in NVMe-MI 2.0 is to make a bunch of interoperability enhancements. Basically, when MI first rolled out, the primary use case was basic health and temperature monitoring using single packet commands with single packet responses over SM bus. And this was pretty straightforward to get working. But then the use cases started expanding and getting more complex. We started doing configuration tasks like managing data at rest protection using TCG-OPAL protocol, which consists of many multi-packet request and response messages that must be done in a very specific sequence. This is much more difficult to handle, especially in a muxed SM bus environment, where the BMC may do a partial command sequence, switch the mux away to manage another device, and then come back later to finish the sequence. We also started doing multi-megabyte transfers, so much larger transfers than we were doing before, both from the BMC to the device for things like firmware update, and also from the device to the BMC for doing things like reading large log pages, such as the telemetry and persistent event log pages. And these large data transfers necessitated the use of higher bandwidth PCI VDMs. And so now we have multiple communication paths from the BMC to the device, which may be occurring in parallel. And also the stakes got a lot higher with the basic health and temperature polling. The commands are less likely to fail due to their simplicity. But even if they do fail, the impact is not usually catastrophic. If you can't get the current temperature, then the BMC could just ramp up the fans to cover the worst case. And if a health poll command doesn't work, well, the typical case is the drive has failed, and so there's no impact. But even in the event the drive is failed, the failure could still be detected and handled in band. But with something like TCG-OPAL, if those commands fail, then you can't unlock your drives, which means you can't access data on the drive, and you can't even boot the system if the drive is the boot volume. So it's absolutely critical that we be able to perform NVMe-MI commands reliably and efficiently. As we enabled these more complex use cases, we ran into interoperability issues caused by a lack of detail in the standard around things like timings and operational states, the various impact of resets. And from a command flow perspective, we already supported a bunch of flow control semantics for reliability and interoperability, but when developing these new, more complex use cases and really stressing those mechanics out, we learned what worked well and what didn't. And so we took all of these learnings and we made a bunch of changes to the MI spec to improve interoperability. And this slide gives an overview of those interoperability enhancements. The MI spec has references to a bunch of external specs, including other NVMe specs and specs published by other organizations such as PCI-SIG and DMTF. And so one thing we did was to go look at all the latest versions of those specs, since they may have bug fixes and interoperability enhancements. We made any changes to the MI spec that were necessary to line up to the latest versions of those specs. And then we updated the references in the MI spec to point to those latest versions. We also fixed a bunch of errata that had been reported since MI 1.2 was published. And then we also made a bunch of improvements and fixes to timings, the command processing, reset handling, operational states, and the status reporting. And I'll talk more about those in the coming slides. And there are also a bunch of TP numbers listed on this slide. A TP is a technical proposal in NVMe that defines new functionality. And the TP numbers here are the numbers of the TPs that implement these enhancements. And I put a link to these TPs, as well as all the other TPs that went into MI 2.0, and a link to the errata documents or ECNs that went into MI 2.0 in the references section at the end of this presentation. So one of the main interoperability issues we had was around time to ready following a power on or reset. In MI 1.2 and prior, we mandated a 1 second time to ready. But what we found is that many devices could not get ready that fast for more complex operations, especially ones that require access to media. And so we added a few new timing parameters where the device can advertise how long it needs to get ready for commands that don't require media access and how long it needs for commands that do require media access. And we permit devices to return a more processing required response until they are ready. And we added a requirement for devices to return an estimation of how much more time they need if they do send that more processing required response. We also had situations where NVMe devices may be unresponsive at runtime. For example, an in-band host may perform a firmware activation without reset, and the NVMe device may be unable to process MI commands until the new firmware is activated. So to handle this scenario, we added a timing parameter for the device to advertise its max unresponsive time. All of these timing parameters are in the FRU data. So the idea here is that the FRU data can be implemented on a double EEPROM or a simple microcontroller that can almost always be ready near instantly via the I2C bus. And then the timings can then be read by the BMC and then used during MCTP initialization to ensure that it's waiting long enough for the device to get ready and become responsive. We also added MCTP timings for things like request to response time, transmission delay, and inter-packet time. We remove timeouts for BMC to device transfers. The idea here is that the BMC is in charge of the communication flows. And so the devices should just wait forever in case the BMC is busy with other higher priority tasks. We also added a parameter for NVMe devices to advertise how long they need to process a firmware activation without reset. There is an existing parameter called maximum time for firmware activation. That one only covers the time that processing of other commands is paused during the firmware activation, whereas this new timing parameter covers the full activation time. And BMCs can use that knowledge of the full activation time to know how long to wait for a firmware activation it initiates to complete. We also specified a bunch of reset-related timings. And finally, we made a bunch of enhancements related to command processing and flow control. For flow control, such as abort, pause, or the flow control primitives, such as abort, pause, resume, and replay. And we made several enhancements to the more processing required response. And I don't have time to cover those in detail, but the details of those can be found in the TPs referenced a couple of slides ago. We also had a bunch of interoperability issues due to underspecified reset conditions. And so we went in and we classified all the different types of resets. We listed the conditions that could cause each of these type of resets and the impact of each of these types of resets on the operation of NVMe-MI. We also made SMBus clock low reset mandatory for MI to allow BMCs to attempt recovery of the SMBus interface after an SMBus related failure without impacting the rest of the NVM subsystem. We also had interoperability issues due to confusion on when MI was required to be operational. MI 1.2 and prior stated that MI was operational 1 second after power on, but many implementations were not operational after 1 second due to conditions such as the device undergoing a reset from the in-band host, the in-band host disabling the controller, the in-band host shutting down a controller, etc. So we clarified that MI was required to remain operational independent of most of these in-band host initiated actions because, where possible, we don't want in-band host initiated actions to impede BMC initiated management of NVMe devices. And we also added clarification on when the SMBus I2C VPD and MUX are available, and we added a boot failure code to VPD that can be used to indicate the failure reason in case the firmware on an NVMe device is unable to be booted. And finally, we hit interoperability issues due to inconsistent and underspecified functionality related to status reporting. We overhauled the status reporting in MI 2.0 to make things consistent, fix errata, and we also added a few new status events to report. All right, with that, I'll move on to asynchronous events. But first, I'll discuss how polling works and some of the issues with polling. So when MI was first introduced, a typical system implementation used SMBus muxes to fan out to more than one NVMe device. BMCs would typically select a single mux channel at a time to avoid address conflicts without having to use SMBus ARP, and to avoid security concerns with attaching multiple NVMe devices to the same SMBus segment. Now, since the device doesn't know if or when it will be connected to the BMC, asynchronous events can't be used. And so instead, polling must be used where the BMC selects the first MUX channel, issues a command to the NVMe device on that MUX channel, waits for the response, and then switches the MUX to the channel with the next NVMe device. And after cycling through all channels on the MUX, the BMC would start over again at the first MUX channel. This, of course, increases the BMC workload, especially for rare events, since most polling commands will just indicate that the event has not occurred. And it may increase latency for event detection, since it may be several seconds for the BMC to get back around to the device that it has had an event occur. And this polling inefficiency is being exacerbated by an increase in the number of NVMe devices that we're starting to see in systems that the BMC must manage. So for example, the number of U.2 drives that can fit in the front of a 2U server is around 24, whereas with newer form factors like E3.S, you could fit 40 or more drives in the same space. And the number of management operations being performed on NVMe devices by the BMC is also increasing, which reduces the amount of time BMCs have for polling. And this added device count and management operations is not limited to NVMe devices. The number of other types of devices and their supported management operations is also increasing, which further overburdens the BMC. But now we have improved topologies. So with PCI VDM and I3C, all of the NVMe devices are always connected to the BMC. So for PCI VDM, the root complex or PCI switch handles interleaving of traffic from multiple devices. And for I3C, the I3C hub handles this interleaving. And so therefore, asynchronous events are viable with these topologies. So due to the inefficiency of polling and the availability of these new topologies, we added support for asynchronous events, out-of-band asynchronous events in MI 2.0. The full list of events is shown in the table on the right and includes events related to changes in health, drive wear, temperature, and inventory. There's also a provision for vendor-specific events. The asynchronous event framework is easily extensible to new events in the future. You'd simply select a new identifier from the range of reserved identifiers, define the scope of the event, and define the trigger condition for the event. And speaking of the scope, the defined scopes are listed at the bottom of the page. Depending on the scope, additional data may be included in the asynchronous event message that the NVMe device sends to the BMC. So for example, if the async event is controller scoped or namespace scoped, etc., then the async event includes an identifier that identifies which controller or namespace is associated with the event. The BMC also has the ability to discover which events are supported and subscribe to only the events the BMC is interested in order to avoid getting asynchronous event messages for things the BMC doesn't care about. There's support for event coalescing and rate limiting. This can be used to limit the number of async event messages sent to the BMC by transmitting multiple events in a single asynchronous event message versus sending a single event in each async event message. This rate limiting avoids flooding the BMC with async event messages for frequent events, but it does increase the latency for those events. However, the rate limiting is adjustable by the BMC, and so the BMC can tune the rate to match the required latency. So, for example, if the BMC requires notification of a temperature change within 10 seconds, the BMC can configure async events to be sent at least 10 seconds apart, and any events occurring during a given 10-second time frame are coalesced and transmitted to the BMC in a single async event message at the end of the 10-second time frame. And finally, we have automatic retries for reliability, and we have the ability to resync in the event that the BMC and device get out of sync. Okay, so on this slide and the next slide, I have example out-of-band async event timing diagrams that illustrate how this all works. Now I'll give a quick overview here, but if more detail is needed, these examples are from Appendix D in the MI 2.0 specs, so you can check there for any added detail. So at step 1 on the far left of the diagram, the device comes out of reset and all asynchronous events, or AEs, are disabled by default, and the device is in the AE disarm state, where AE disarmed means that any events that occur will not result in the device transmitting an asynchronous event message, or AEM. There are standard commands that allow a BMC to determine if asynchronous events are supported, and if so, which ones. And once the BMC determines which asynchronous events are supported, the BMC can enable those events that it is interested in, as shown in step 2. And once the BMC sends the command to enable AEs in step 2, the device responds back with the current state of all the enabled AEs, so the BMC and device are in sync on the state of everything. And then the device enters the AE arm state, meaning any events that occur will result in the device transmitting an asynchronous event message. And the device also starts an AEM delay interval timer, whose value is adjustable by the BMC. This is the rate limiting feature we discussed earlier, where events that occurring during this time period will be coalesced and sent as part of a single AEM at the end of the interval. Now, step number 3, we have our first asynchronous event occur, but an AEM is not yet transmitted due to the delay interval. And at step 4, we have a second asynchronous event occur, but again, an AEM is not yet transmitted due to the delay interval. At step 5, the AEM delay interval ends, and the device enters the AEM transmission interval, and it also enters the AE disarm state. At step 6, the device transmits the AEM containing asynchronous events number 1 and 2, and it starts an AEM retry delay timer, This AEM retry delay is also adjustable by the BMC, and it's the amount of time the device waits to get an acknowledgement from the BMC that the BMC received the asynchronous event message before the device will try to retry transmission of the asynchronous event message. Now, at step 7, we have a third asynchronous event occur, but we're in the AE disarm state, and so no AEM is sent. And we'll see how that asynchronous event gets communicated shortly. At step 8, the device times out waiting for an acknowledgement from the BMC. And so in step 9, the device retransmits the asynchronous event message for AEs 1 and 2. And this is just a replay of the original asynchronous event message. And so note that it still doesn't include asynchronous event number 3. Now, at step 10, the device finally gets the acknowledgement from the BMC that the BMC received the asynchronous event message for AEs number 1 and 2. The device transmits a response to the AEM ACK, and any events that occurred during the current AE disarm state, which is AE number 3 in this example, are transmitted back to the BMC as part of the AEM ACK response. So that's how that third asynchronous event is handled. And then finally, the device transitions back to the AE arm state and restarts the AEM delay interval, and the whole process starts again. Now, as part of the AE setup, the BMC and NVMe device synchronize the state of events. So the device tells the BMC the current state of all events the BMC enabled, and the device is required to notify the BMC of changes to that state via an asynchronous event message. But the BMC can get out of sync if, for example, the BMC was unable to receive async events due to some error condition, due to the BMC being reset, etc. And so if this occurs, the BMC can resync using the same commands it used to do the initial setup and synchronization, as shown in the timing diagram on the left. So in this example, things start out the same as the prior example, but asynchronous event number 1 occurs after the AEM delay interval at step 2. And so the AEM for that is just sent immediately at step 3. Now, in this example, the device never gets the AEM ACK from the BMC, and so it retries until it exhausts the retry attempts. Per spec, the device is required to attempt 8 transmissions before finally giving up, which it does at step 7 there. At step 8, we have another asynchronous event occur, but it occurs during the AE disarm state. And so again, no AEM will be generated for it. And at this point, if the BMC comes back online, it may end up waiting forever for an asynchronous event message that will never come. And so if the BMC is unsure of the synchronization state, the BMC can perform a resync to get that current state and start everything fresh, as shown in point number 9 there. All right. And with that, I'm going to turn it over to Myron to talk about high availability.
Thank you, Austin. Thank you, Austin. Yes, let's talk about high availability, the third topic, I guess, for today. And high availability is a smaller subset of the NVMe ecosystem. And it's basically people are willing to pay a lot more attention to detail here to make sure that they never ever lose their data. They want to keep their data always available to whoever needs it. One of the methods that people use for that, well, you can like geographically diversify, and you can have redundant copies, right, that you steer the people to all around the world. But one of the common methods is to put 2 hosts into a box, and they can both talk to the same SSD. And so host A can access some content on that SSD, and host B can access some same content on that SSD. If one of those hosts for some reason has a crash or needs to be updated or something like that, that host can be taken offline, and the other host can still continue to access that data. In some cases, you might be able to swap out the host that failed and put another one in and bring everything back up alive again. Other cases, you may have to do some controlled slow shut down in the background when it's an off time. But in any case, the purpose is that we get rid of a bunch of the failure points and make them redundant, and thus we can have more consistent access to the data. So in this scenario, we still want to be able to manage that SSD. And so now you have these two boxes that both have to talk to this SSD, find out if there's any alarms going off, anything that needs to be known about the SSD. So you got the BMCs on each host is the blue box kind of on the outside where it says management controller, BMC. That box can talk through the PCIe path you see in kind of a pinkish purplish color. And you can see how it goes through PCIe port directly through those lanes. The PCIe port, the SSD probably had a four lane PCIe connection in this example. It was bifurcated in half using the dual port enable. And now each host A and host B each have their own two wires to talk to that SSD. So the bandwidth is smaller than we had before, but it's still sufficient, and total bandwidth to the namespace is still the same. But now the out-of-band traffic is tunneling through the PCIe bus, and this management controller can talk to the namespace or talk to the storage device, and it can fetch temperature, for example. And if the temperature is going off the rails, it can turn on some more air and keep the thing cool. If something else goes wrong, it can alert somebody who can go and swap out failed components. But what the complicated part is that if they use the SM bus path, which is in the green, it goes around the bottom, those two paths collide at the bottom of the screen. The arbitration's out of scope here, but eventually the traffic gets back up into the SSD at the bottom. And now if one management controller is sending a command to the SSD and the other one wants to send a command to the SSD, they have to synchronize outside, and see the blue on the very top. They have to take turns because they can only talk to the SSD one at a time. And in addition, if there's some resource on the SSD that they're trying to both manipulate, like a status bit for the temperature, right? So you set this flag when the device goes over temperature. If one reads it and clears it, the other one will never get that alarm. So let's look at some solutions here, how we've tried to fix that. So MCTP already defined a method for bridges to have more than one endpoint. So what a bridge, don't have a good picture here for that, but a bridge would take one upstream path and fan it out to a bunch of downstream devices. When the bus owner, in this case it's the BMC, would send a set EID, so basically it's configuring, enumerating the bridge and gives it an EID address. So if we look at the first bus between those two blue blocks is the D1P1 or D1P2. That one is assigning endpoint ID 12 to that bridge-like device. And when that happens, the bridge would send back a response saying, yep, I took number 12, and I have this additional addresses you can assign for all that's downstream the fan-out devices. It would say, maybe I have 4 ports that you can give me 4 more addresses for. And so we're going to use that same mechanism, so we didn't have to change the spec at all. We're just kind of defining a new use case for what the spec already had written. And we're not going to say we have 4 downstream fan-out devices. What we'll say is we have a pool size of 1. And so that way the bus owner, in this case the BMC, would say, hey, I can give them 1 more EID. And because the bus owner already knows it's an SSD, it will understand that 1 extra address is another port into that same ecosystem. And we'll just show you a picture of that coming right up. But I just wanted to clarify here that it doesn't change the MCTP protocol at all. And it's not really a bridge, but it uses the same mechanism as a bridge. This is to make SM bus work, but it works the same with I3C and with PCI VDMs and other MCTP bindings. So let's look at the next picture and see how this gets used. So here we're back to that same picture we had before. And the pink line doesn't change at all for the PCIe bus, but the green line coming down around the bottom now comes back up into the SM bus port. and you can see it goes to 2 SM bus management endpoints. They're both at the same physical address on SM bus 3A, but now there's 2 complete state machines inside. There's EID 12 and EID 13. And so that's something that would have been impossible before. And probably the other neat thing to take away from this picture is all those status, the kind of the yellow status blocks inside. That this before we had the multiple ones per control, but some other changes were done, and Austin kind of highlighted this earlier, is that we clarified how the status works, and these are completely redundant copies of status. So each controller up above in the top of the darker blue box has its own status. Each PCIe VDM had its own status. That was before already the case, and now each of the green boxes at the bottom has its own status. So you can see that the SSD has to keep track of a lot more statuses, but the status is typically all the same. Like the entire SSD as a whole changes into an alarm condition, but there are some statuses that also change per controller, and that's, well, I guess the key here is now that host A and host B can independently access them. In addition, well, let's not get into more technical content there. I think that's enough for this level. And go on to the final topic. All right, so for I3C, the problem that we had, well, there's kind of 2 problems that we had. So Austin had this picture already earlier when we talked about the mux in the middle of the trapezoidal shape there, where the mux switches the BMC to connect to one SSD, then another, and it kind of goes through this loop and talks to each one individually. And so that's one problem, is that when the SSD is disconnected from the BMC, it can't send a message back to the BMC saying, hey, I got some kind of alarm condition. It has to wait till the BMC switches back to it and connects to it again. The other thing that Austin brought up earlier is that we are doing a lot more complicated work on the SSDs, and a lot more traffic is being sent back and forth with like huge things like firmware images and log pages, and these take minutes to transfer at SM bus speeds. So to fix that, we're going to kind of go through a roundabout path, but in the end, we're going to fix this hub. Sorry, this I3C MUX will become a hub. It's a new an architecture defined by the industry that's a pin-compatible parts you can buy from Renesas and from TI, and it connects the SM bus and I3C signals all the time from the BMC to every SSD. So any SSD that wants can just start talking. As long as the bus isn't busy, the traffic will get back to the BMC. If it's busy, it just backs off, waits till the bus goes idle, and it can try again. All right, we aren't going to talk too much about the hub. We're going to look more at the protocol, the I3C traffic. That's the next slide. So MIPI defined this upgrade to SM bus probably a couple of years ago now, but it had been over 30 years since SM bus was updated. So I3C is kind of the next phase on top of that. And just to be clear here, if we remember back at the prior feature when we talked about the high reliability, that there was the PCIe path. The PCIe path is still much faster than even these improvements. And so companies that use the PCIe path, they don't have to have the SM bus path for these improvements, but it's more so for companies that don't have the PCIe path. So the I3C improvements over SM bus. There's a whole list here. We're not going to go into deep detail here on each one, but that's much faster. So let's say it's about 100x faster, maybe 50x, depending if you're not getting the full speed out of the I3C and you were running your SM bus at 400 kilohertz. But everybody has their own I guess, study to do how much faster it'll be for them. But let's say it's about 50x faster and about 10x lower power. And we're going to talk about the reason for that here in just a second. Let's jump to that right away. The picture at the bottom shows a typical trace that you might see if you put your scope onto your SM bus wires. And I3C looks exactly the same. That's why we say it's backwards compatible. The signals and the addressing, those first 7 A0 to A7, or sorry, A6 bits are the address that's being sent down the wire. And then, so whoever's the transmitter would send the address who it wants to talk to. Then the receiver sends the ACK back right in the middle of that diagram. And then it would send the transmitter would continue sending the data. So the start condition is the same. Everything is the same for I3C. This exact picture works for SM bus and for I3C. But if you look at the far right-hand side where it says 0.7 and 0.3 times VDD, that's highlighting that the signaling now is going to use standard CMOS voltage levels instead of SM bus before had a threshold of 1.25 volts, and that's all kind of changed to make things simpler and work better with modern lithographies. We can go to lower voltages. We can actually run the entire bus now below 1.2 volts, probably down to 1.0 volts. But in this case, we chose 1.8. Then the other thing that you can note here is that there's curved lines on all of the A bits. That's because when SM bus would start talking, it would have to be able to handle a collision. So if two different things are talking at the same time, because you don't know who's going to jump on the bus first. So the way they did it is they just use an open collector, so it was safe. Anybody could just pull down the wire, and that would show that they were starting to talk. And then when they let go of the wire, it would be pulled back up with a resistor. And that's why there's a curve going up slowly, because that resistor, you scale that resistor for whatever you want for your baud rate. But it made it safe, so anybody could talk at the same time. So I3C said, hey, well, let's take care of all of the bus collisions right during the address byte, so that part looks the same. But then after the address byte, the data bytes 7 bits, D7 here is the first one. You see that the edges get squared up a lot. And that's where the bus changes from an open collector driver to a push-pull driver, and it's forcing the wire high. At this point, at that acknowledge point, it's only possible to talk to the addressed device. All the other devices should be gone. There's no need to worry about collisions anymore, and thus we get the higher speeds of using the push-pull. And what you'll often see in I3C traffic is that the address will be sent at a slower speed, still much faster than SM bus, maybe like, let's guess, 2 to 4 megahertz. And then the data traffic coming afterwards will go even faster, up to 12.5 megahertz. And so that we've talked about a lot about the how the signals look on the wire. One thing to note here at the very end, you see a little T on the data line. The ACK bit has changed to a T bit. So the ACK bit for the address is still the same, but then after that, instead of reversing the bus back and forth to send acknowledge for every byte that you receive, to keep the traffic going faster, they didn't have time for the bus turnaround. So now the transmitter, whoever's talking, will also send the T bit. So whoever sends the data will send the T. If it's the command coming from the BMC to the SSD, the T will now be parity for those last 7 bits. Every 7 bits gets a parity, so we add robustness. It's in the reverse direction. When the BMC is reading the data from the SSD, then the T bit will mean whether there's more bytes yet, or more bytes or bits, more content yet to come after that. Right, so it'll basically say keep reading, keep reading, keep reading, and all of a sudden at the end it will say, oh, I haven't got anything more, and then that will stop the transaction. Another thing that SM bus had is it had separate wires if you wanted to send interrupts or resets. And so even though we had defined the SCL clock low reset before, if you held the clock for 25 milliseconds down, other people did not have that. And so I3C defined in-band reset pattern and also in-band interrupts. Both of those are just patterns or mechanisms of using the same 2 wires to do interrupts and resets. And then the final thing on I3C is that it has a bunch of command codes. So tasks that everybody has to do, like setting up address or grouping a bunch of addresses, or discovering what was plugged in, what its capabilities are, how fast you can talk to it, how big a data packet you can send it, those kind of things are all going to be common commands. Before we had to do those things at the MCTP level, now they're moving down into the physical layer. And here's a quick picture of how that traffic looks. So MIPI defined the I3C protocol itself. DMTF built a binding spec on top of that for how to send MCTP traffic. We won't get deep into that here today, but there's some pictures. The very top purple traffic is a message from the BMC to the SSD. You can see it sends an address, and then there's an MCTP packet inside of it. Then one thing that we didn't talk about I3C is that only the BMC can drive the clock. So this adds robustness and security, right? So that the peers can't talk to each other. But the way that a peer wants to start talking is it sends this interrupt, which is its own address. It sends traffic to its own address back to the BMC, who then sees the traffic and then says, hey, I got an interrupt from that device. And the AE says that it's right in the middle of the second purple row. The AE says that it's an interrupt from an MCTP packet being pending, ready to read. Then the final purple line is that the BMC reads that with a private read, and you can see there's another packet embedded there, an MCTP packet embedded in that response. And that is the response for the first command. So we didn't get time here to dive deep into all the cool stuff that DMTF added to MIP to I3C, but you can do that if you read the DSP0233 spec from DMTF. And going into the slide here on PCIe. So I don't want you to read this whole eye chart here, but PCIe defined this flow chart for how we negotiate what, well, they also changed the name from SMBus to 2-wire, and then how to negotiate whether that 2-wire will be in SMBus state or in I3C state. And it uses the 7E address, which is reserved for SMBus. But if an I3C device sees it, then it will the first instance of the 7E will turn off all SMBus ports on the I3C device so that the BMC can check if there's anybody that's incompatible left on the bus. And if not, then it will send the 7E again, which will force and switch the bus from the 3.3 volts down to 1.8, which is important for all future lithographies that can no longer do 3.3 volts. And then it will start sending MCTP over I3C traffic. And note here that old tasks that you used to do over SMBus no longer work, like an I2C through read or the Appendix A traffic. Those won't work at I3C speeds and voltages. And then if we get a reset, it will return us back to SMBus mode. So if we accidentally go there, there's a recovery path. So this was all adopted by NVMe in the version, the 2.0 spec that we were just talking about today. And you can read TP6037 if you want to get just these details, but it's also part of the regular spec. The things to note here is that if I3C is supported, then it'll be discoverable at either the NVMe-MI data structure or the free information device, similar to those timings that Austin talked about earlier. And a few things that happened here is that the MTU, we used to have a command for it in NVMe to set up the MTU size for SMBus. That now has a mechanism in DMTF, so we're using that mechanism instead. And another thing to note here is that the hot join protocol from MIPI's spec is not permitted during NVMe-MI operation. And finally is that we clarified the type 2 reset from MIPI, so that instead of it being a whole chip reset, we're specifying that it's the whole MCTP endpoint controller reset. It doesn't reset the SSD itself. And then there's a bunch of examples in the content there. You can see an example here below. Example 13 is what the packets would look like, or what the bytes being transferred are for an NVMe data structure read. And we won't get to that, but we will jump to the final slide here, which is a bunch of links, so you can go and read a bunch more material yourself, and then we can open up to some questions.
Great. Thank you so much, Myron. We'll go ahead and kick off the Q&A now. So please go ahead and share any questions you may have in the questions box for our speakers, and we'll go ahead and address those. So the first question that we have today is it possible to overflow an asynchronous event message if there are too many events in a given AEM delay interval?
Yeah, sure, Nolan, I can take that. So yes, we if you had a whole bunch of events, in theory, you could overflow the size of the asynchronous event messages in NVMe-MI are limited to around 4K. But if you had a simple device, so it's just a single controller, you're really unlikely to overflow. But one thing we did to alleviate this issue that I didn't talk about is, if you have multiple different events, they all get wrapped up into a single asynchronous event message. But if you have multiple occurrences of the same event, we don't put a different asynchronous event for each of those. We only transmit back the most recent one. So if you're in a delay interval and the temperature changes from, say, 25C to 26C, that's an event. And if it goes from 26 to 27, that's an event. But when the message gets sent back, it'll just send back the most recent occurrence, which would be the current 27 degree temperature.
Great. So our next question is, what's next for NVMe-MI?
Yeah, I could probably start here, then Myron, you can add if you have anything. So we have just finished putting out NVMe-MI 2.0 this summer, and we have a lot of these new features that we discussed. So I think probably right now what we'll be focused on is enabling all these features in the industry. So getting this support in the BMCs and into the devices. There's other standards out there. Like most of these features are optional, but there's other specifications. Like if you go look at the OCP data center NVMe SSD spec, it has requirements to implement a lot of these features for use in enterprise and hyperscale use cases. So we'll focus mainly on getting all of the existing features implemented. And then there are some other new use cases that are being worked on, driven by some of, mainly by like our cloud use cases. For example, where folks want to allow tenants to have bare metal access to servers, but they don't want the tenant to be able to change certain things on the NVMe devices. Like they don't want them to be able to change firmware and these sort of things. And we have this existing mechanism in NVMe and NVMe-MI today, where a BMC can go in and lock out the host from being able to do these types of operations. But there's going to be some improvements in that area that we're going to be working on. I don't know, Myron, did you have anything to add there?
Yeah, that was a good answer. I think maybe, just as whenever time we ramp up the ecosystem on some new features, there's always some maybe gotchas in the spec that we have to explain better, or even just things that we didn't comprehend the first go at a new feature. And so there'll probably be some continuous improvement to the existing things that we were just talking about today.
Great. I think we have time for one more question. So for the last question, can SM bus devices and I3C devices participate on the 2-wire bus at the same time?
Sure, thanks. That is a bit of a nuanced question. I talked a little bit how discovering if they're both on the bus at the same time, but I didn't get into that particular problem. If the SM bus device and the I3C bus are on the same segment of the network, then that segment is limited to the speed of the slowest device. If, as we saw in the picture, there's a bunch of SSDs hanging below the hub, different streams below the hub can all operate at their own speeds. But if there's multiple devices on the same port of the hub, that would limit it to the speed of the slowest device.
Excellent. So that was the last question that we have time for today's webinar. So thank you to our speakers, and thank you for everyone for joining the webinar. If you'd like, the webinar video will be available to download and to view on our Bright Talk channel and to view on our NVM Express YouTube channel as well. The slides will also be made available on the NVM Express website for downloading. And thank you everyone for joining.